right. Tell your neighbor what you think.
On the test, solid test.
Correct answer is? Correct answer is A. Now, voltage is the push. It's the motivator. That's what causes current to flow. Good with that? So here's some terminology, and don't worry about reading the question. So there's certain parts of the circuit that give energy, and there's certain parts of the circuit that take energy away. That when I talk about take energy away, I'm talking about there's at a certain point in the circuit, they have a certain electrons have a certain amount of energy, like has a certain amount of potential, has a certain amount of energy per electron, and then as it goes through the circuit, that electric potential energy is converted into a different type of energy. In this case, well, like what part of the circuit uses or converts electric potential energy to some other type of energy? The battery or the light bulb? Probably the light bulb. It's like what we're doing with the circuit, trying to turn on the light bulb. Okay, so the light bulb is where you have an electric potential drop, a voltage drop, because it uses some of that energy to make heat and light. Okay, so right here, there's a certain amount of energy per electron, and then as it goes through the light, it contributes that or converts that electric potential energy to other types of energy. So here, the electrons don't have as much energy per electron. There's an electric potential drop or a voltage drop across the light bulb. You all right with that idea? Versus voltage gain. It's a section of the circuit where energy is given to electrons. And that would be what? The battery or the light bulb? Everybody okay with the battery? Giving it electrons or giving energy to it. So from here, it doesn't have much energy per electron, but on this side, it has a lot more energy per electron. So across here, there's a voltage gain, potential gain. Just trying to teach you some lingo. Mm-hmm. Yep. So the battery in this circuit, in this cycle, energy is given to electrons from here to here. Good with that? Thumbs up when you have a guess. Correct answer is D. Dangerous dinosaurs. which is surprising to a lot of people. So this fact is also true for rivers or creeks. So long as you don't have any like other rivers or streams contributing to it or taken away. Like if you just think of a river, so the current in a river at all points is the same at other points. So long as you don't have things adding to like tributaries, other creeks and stuff. So here's the idea. Current is not how fast the things are moving. It's about the amount of things moving by a certain point every second. So if here's your river, here's upstream, here's downstream. Okay. If there was more water flowing by this point per second than this point, what would happen would be there would be flooding here. Does that make sense? If there was more water flowing per second here than here, what's going to happen is this is going to be like where'd it go? Just dried up. It's like because there's more leaving than coming. So in order for a river to flow, there needs to be just as much water going by this point every second as this point every second. But then you're like, but every time I've been on a float trip or a canoe trip, the water's moving at different speeds, right? Depending on where you are in the river. And I say, yes, that is very true. But current is not about how fast the particles are going. It's about the amount of particles. So in your experience with canoeing, floating, your experience on the river, how would you describe the riverbed when the water is moving fast? When you get ripples, when you get like rapids, they're shallow. So what that means is, in order to get the same amount of water going by a certain point every second, the shallow parts, there's not much room. And so the water has to be moving quickly. You get that much water past that point every second. Versus the deep areas, that's when the river is going slow. But it's the same amount of current. Okay, so here, regardless if you have a single path, the current at every point along here is identical. You all right with that? Just thumbs up when you have a guess. So I'm just going to give you the answer to this one. Correct answer is C. Only C. Crazy cats. This not true. The light bulb doesn't eat electrons. The filament, that's the skinny part. This actually is like on the river, the shallow part. So electrons are actually moving really fast through the filament. Okay? But they're converting their potential energy to heat and light. Good there? All right, so talking about resistance. So let's just think of copper. Copper wire, that's like the go-to material for wiring in residential houses. Do you think a long copper wire or a short copper wire is going to have less resistance? Just intuitively, hopefully your intuition says short is going to be less resistive. So if you have to pick between two extension cords, one's 100 feet long and the other one's 20 feet long, and you have to go from here to across the room, which is 15 feet long, hopefully your brain would say, you know what, I should probably choose the 20 because the 100 just seems like a waste. There's more energy being lost because it's longer, there's more resistance in a longer wire than a shorter wire. Everybody okay with that one? That one usually isn't too hard to swallow. Thick wire versus a thin wire, which one's going to have less resistance? So here's a leading question for you. Which hose is going to be able to pump more water out of it? A garden hose or a fire hose with the same amount of pressure? Fire hose, a thick diameter, is going to have less resistance because it can get more electrons by a certain point every second compared to a thin one. Okay. And so the thicker the wire, the less resistance. If you go to a hardware store and you're shopping for wire, it's going to be rated on gauge. The lower the gauge, the thicker the wire. Okay, kind of like ear gauges. The lower the number, the bigger the gauge. Think of gauge like as a measure of resistance. As the gauge number goes down, so does the resistance. Good with that? Okay. Huh. Mm-hmm. Right. So if you had, a certain material is going to have a certain resistivity is the word, okay? But if you have to go through that same material, but a longer path through that gauntlet, an electron is like, oh my goodness, are you kidding me? So there's going to be total resistance. I'll show you the equation after we go through this. Actually, I can show you now that so the actual equation, I'm not going to make you calculate this. But that's the resistivity. That's like what the material is made out of, times the length. So the longer the length, the greater the resistance over the cross-sectional area of the wire. So the bigger this is, the less this is. Okay. You're not going to have to use that equation, but that is the equation. Okay. And then hot wire versus cold wire, which one's going to have less resistance? One might think hot wire has less resistance because, like, hey, look, it's hotter. Electrons can move better. Things are able to flow better. That's true, but that's not the only thing that's moving more. As you heat it up, the atoms in the wire also vibrate more. And so it causes the electrons to get thrashed. The gauntlet that goes through it just gets way more violent. And so hot wires have more resistance, cold wires have less resistance. That is why we put what on electronic devices? Cooling fans. Okay. Some hardcore gamers actually refrigerate their CPUs, like have cooling devices, like going through, just like bring it down, and like just so we could take the resistance down just a little bit more, less lag, get the edge. Okay. Get to that. Are we okay with B, the skinny filament, as a smaller diameter? So this is the old school light bulb. Since this point, so this is like the same thing Thomas Edison, like we still use it. Some people like that's the thing, but we switched to fluorescent. That's like the long tubes are the ones that are the swirl, the curly spiral light bulbs. And then we've now switched to LEDs, which are like the up and coming. I think they'll be here to stay for a long time. Type of light bulb. Okay. Thumbs up when you have a guess. Tell your neighbor. Did everybody go with A? Okay. You got hot. Sorry. Temperature goes up, so the resistance also goes up. Okay. But sometimes this brings up the question, like, you know how your car on cold winter days is hard to start? I know you've probably never left your phone in your car on a cold night. I mean, that would be like forbid. Like, but let's say you left your calculator in your car overnight, and then you go to start it up. I don't know if you've ever seen electronic devices struggle when they're cold to start up. It's like, go. Okay. What are all those devices powered by? What's the power source for all those struggling devices? Car, phone, calculator, computer, batteries. Inside a battery, there's a chemical reaction. What happens to chemical reactions, the rate at which reaction take place as temperatures go down. So Gagnon's people, is that a thing? Temperature rate of reaction decreases. Someone said brownies. You guys made brownies or something.
But you made no connection to that.
Literally just made brownies.
You made brownies?
Yeah.
I was thinking we'd have some redemption. We just ate brownies. So, ready? Here's some chemistry knowledge. Really important, very practical. As temperatures go up, the rate of reaction, how quickly the chemical reaction takes place, increases. As temperatures go down, it slows down that, how quickly that chemical reaction proceeds. Good with that? That's good tidbit of what you should have learned in chemistry. Okay, good? I'm just going to tell you the answer to this one. Correct answer is C. Okay. This is talking about like what will come out of, that's current. That's kind of describing current. That's not voltage. This is what you're going to learn about on the pre-quiz tonight. Different concept. This is your how you would describe what voltage is. Okay. All right. Thumbs up when you have a guess. Have a conversation. What do you say? Correct answer is B. Beautiful butterflies. Okay. Voltage does not flow. It pushes. Okay. Current is what flows. Good with that? Okay. So voltage provides a lot of pressure so that it will cause a lot of current. Okay. So I don't know if you ever heard this expression, current is what kills. Okay. We've learned last chapter that voltage doesn't kill you. We had the Van de Graaff generator is like 100,000 volts, like crazy amount of voltage, but we're still here. Like there was some discomfort, but it wasn't really that bad. Okay. High voltage will allow for a lot of current when we're talking about circuits, circuit electricity. So if you have 1 milliamp of current flowing through, it's like, oh, there's something there. 5 milliamps, like, ouch, that kind of hurt. 10 milliamps, your muscles are spasming. So like, I don't know if you ever done that, like shock therapy, like muscle conditioning type. In college, I had a roommate who was a physical therapy major, and he brought one of these devices home, and it was awesome. Like we hooked it up. I hooked it up on my quad, and just cranked it all the way up. It was like so painful, but it was awesome at the same time. You could like see my muscle totally flexing. It's like, oh! Now I'm guessing that was like in the 15 milliamp range. But super cool. If you have 70 milliamps going through your heart for more than a second, it's going to be fatal. This is different than the defibrillators, the clear. Okay, those are like a static shock. It's a surge, just all of a sudden, boom. Okay, it's not a continual. And those are used for like last resort things. Just, you're not like, I've got a headache. I should probably get shocked. Like that is like, it's like your heart's doing something. Like do something, or the guy's gonna die. Like last case, and maybe it'll reset it. Boom. Like nope, do it again. Boom. You're just trying. So you're trying to reset the signal for your heart because your muscles work by electric stimulus, like electric signals from your brain to contract. Good with that? Thumbs up when you have a guess. Have a conversation. Okay. At the end of the day, here's what determines if the bird lives or dies. If there's an electric potential difference from one foot to the next. If there's no difference, there's no motivation for the electrons to go from, like from one foot through the bird's body into the next. So correct answer for this is E, all of them. Okay. So when they grab onto one wire, the electrons are like, why would I want to go through the bird's body to get to this foot when I could just go through the wire? So one single wire, you're fine. If the bird straddled and touched from one wire to the next, there's probably an electric potential difference from one to the next. And the electrons are like, whoa, that looks way better over there. And bird goes poof. Okay. Or if the bird's touching the ground, the electrons would rather be in the ground, and so they'll travel through the bird's body to get there. Good with that? That's why you should never touch a downed wire. Other than the sparks and everything, it looks really dangerous. Like, probably shouldn't touch that. Okay? So, the third prong is a safety. It's called the ground wire. Here's how or why we have this. So, let's pretend we didn't have the third prong. Your device will work just fine. Okay? But so let's say we had a washing machine. So over time, there's sometimes where your load gets off-centered and it's like it shakes a bunch. So let's say over the shaking process, the wire was being scraped on by the metal frame, and over time, it starts to whittle away the casing of the wire, the insulation, to the point where it's touching the metal wire. So all of a sudden, your metal frame is touching the copper wire, and so your washing machine usually has like insulated feet, and so the electricity can go into the frame, but then it can't go to the ground. But then when you touch it, it's like, ooh, look, poof, past the ground, and you get shocked. Okay? So the ground wire, I don't know if you've ever done any like wiring or not, but like there's a wire that's completely bare. That's your ground wire. And when you put it up, when you plug it, like connect it electrically, you actually physically bolt it to the metal casing. Like that's it. Usually there's a green screw, and it just sits there. Okay. The other side is connected literally to the plumbing in your house, which goes to the dirt, the ground. So it just sits there just in case this type of thing happens where the metal case touches the exposed wire, and so the electricity is like, ooh, look, past the ground, and it trips a circuit breaker, but it doesn't kill you. And when your circuit breaker trips repeatedly, you're like, something's fishy here, and so you start investigating. You're like, whoa, look at that exposed wire. Good thing I didn't touch. Oh man. So your devices will work with or without there. That's just a safety device in case that happens. Okay. Thumbs up when you have a guess. For the sake of time. And the correct answer is B. So the power supply determines the voltage. This is still going to be 120 volts. So you're connected to the outlet. Okay. So to make it go brighter, you need more current. In order to make more current, with the voltage staying the same, your resistance needs to be less. Okay. Thumbs up when you have a guess. Correct answer is B. Bountiful buffaloes. Okay. Here, the voltage is determined by the battery. You still have 1.5 volts. But this is a complete circuit, but does not have much resistance. This is known as a short circuit. You ever heard of that? Like, oh, it got short circuited, or something like that. It's a complete circuit, but there's no real big resistance here. So the current's really high, and it can fry stuff. Okay. So if we include the light bulb in the circuit, I'll give you a hint. Correct answer is E. Figure out what is the correct combination. Tell your neighbor. Correct answer is voltage stays the same. It's still the same battery. Including the light bulb, our resistance goes up. Therefore, our current goes down. Good with that. Okay. So when I was a kid, we'd have to jump start our car occasionally. And I knew like our jumper cables were metal. I knew at that age that metal is a conductor, and like my dad's like, don't touch them together. Like, what happens? And I'm like, that happens. I'm like, I'm touching metal. Like if I like, ah! Just kidding, nothing happens. Why am I safe touching metal? Like what's the voltage on a battery, car battery? 12 volts. It's not enough pressure, not enough push. My head is too resistive to have any considerable amount of current. Wouldn't recommend licking it, but good at that. Okay. The last thing I'll leave you with is how to jump start a car. If I run out of time, the idea is red on red, black on black. Okay, so here's how you do it. If you're just a little bit dead, you can just hook red on red, black on black. But here's your running car. What you want to do is connect to this guy to the positive. This is like the safest way to do it. And then red over here, and then black, black on here, and then finally black on a frame of the car rather than the terminal. The reason why is because it produces hydrogen gas, and there is a slight chance in the sparking as you connect it, it ignites the hydrogen gas. I've never seen that happen ever, but that's what they say. So there you go.